So hi everyone, I'm Luke Marsden from HelixML, and I'm really happy to be here today with Diego. Diego, do you want to introduce yourself and say a few words about what you're working on?
Yeah, sure. So I'm from INFN, that is the National Institute for Nuclear Physics in Italy. And I'm here today mainly because I'm one of the maintainers of the Interlink project, and we will see during this recording how it works and why we are integrating it with Alex. So
Awesome. Yeah, thank you so much. So I'll just share my screen and show a little bit about kind of what we're working on from Helix perspective, and then talk about why we're so excited to be working with Interlink in terms of getting Helix working really well on HPC infrastructure like Slurm clusters. Um, So yeah, very just to kind of give a brief introduction to what Helix is. Helix is a private Gen AI stack, which another way of thinking about that is it's like a version of OpenAI and ChatGPT that you can run locally on your own infrastructure. So we have this software stack that has a notion of GPU runners kind of at the bottom of the stack, and those GPU runners can be provisioned from anywhere that you can run containers. And in particular, what we're going to show today, they can be provisioned from Slurm clusters using the Interlink stack, which bridges Kubernetes into HPC infrastructure, if that's a correct way to describe it. Um, and that is super cool because it means that you can then deploy these ChatGPT-like or Bedrock-like interfaces that allow you to do LLM inference, image models, fine-tuning, RAG, API integrations, and all of these things that people want to do with large language models on existing HPC infrastructure, which currently isn't set up to enable those kinds of capabilities. So, so yeah, we have this piece in terms of this GPU scheduler where you can have many GPUs attached, and Helix will automatically kind of bin pack the model instances, like the large language models, across those GPUs. We then have this kind of lightweight control plane that does multi-tenancy and authentication using Keycloak that can be integrated with like Active Directory or LDAP or whatever your organization is using for single sign-on. And also provides sort of external APIs like an OpenAI compatible API. And then on top of that, and the web interface is a core part of the control plane as well. And then on top of that, we have these kind of three pieces, the models. So we have all of the best, latest open source models like Llama 3.3 from Meta, and Qwen 2.5 from Alibaba, and many other high quality models, including ones from Mistral. And then the ability to integrate with knowledge. So you can bring your own documents and knowledge bases that the LLM applications that you build on Helix can refer to. So they can have specialized knowledge to your domain. And then we also support this kind of API integrations piece so that you can plug your applications that you build into any external API. So you might have Jira for managing your software projects. You might use Confluence as a wiki, and you can give access to those systems to the applications that you build and the models that are running on these GPUs. And then on top of all of that, we have this kind of AI apps abstraction. Um, we're working on a standard for that called the AI spec. But the core thing about that is that you can both build these apps by clicking buttons in a web interface, like you can with the GPTs feature in ChatGPT. But you can also export those applications as version controlled YAML files. And those YAML files can then be versioned and managed almost like, well, exactly like Kubernetes objects. And also they can be treated as in the same way that you treat regular software when you're doing software engineering and DevOps. And another key feature that we've recently added is the ability to add tests for these AI applications. And so you can specify a sequence of tests, and then automatically run those tests in CI every time you make a code change. So what we're going to do today is we're going to try and stand up this entire stack on a Slurm cluster on a supercomputer in Italy. And then we're going to try and show you all of these different pieces. So that should be fun, Diego. I'm looking forward to it. Um, oh, you're on mute. Sorry. I can't hear you. I can't hear you, Diego.
Oh,
Oh, sorry.
yep. Maybe with my mic turn on is better. So,
Yeah, yeah, no, it's fine. Totally fine. Yeah, just say whatever you were going to say again. That's fine.
yeah, sure. So the problem, my comment was about the supercomputer is is in Slovenia and is part
Ah,
of the European project that we are going to use and to exploit that technology. So Intertwin is born essentially in the context of the Intertwin project. So we are
cool.
leveraging this project to access the various HPC provider, and the one of today is Vega supercomputer in Slovenia.
Okay, cool. So why don't we just re-record that whole bit where I
Yeah.
don't say wrong that the supercomputer is in Italy?
Yeah, exactly.
Yeah, yeah. So what we're going to do today, Diego, is actually try and set up this Helix deployment on a supercomputer, and we're going to then try and show all of these different features. So do you want to start by talking a bit about the supercomputer that we're going to deploy onto?
Yeah, sure. So we are going to explain the supercomputer thanks to the collaboration, and actually the catalyst of the InterTwin project was the European project called InterTwin. That it's the ambition there is the create an ecosystem of digital twins engine. So machine learning and AI accelerated stuff to create reproducible scenarios of real case environments. So
Hmm.
simulating floods and whatever. So, and to do that, of course, you need resources. So in that project, Vega HPC Center, that is the one that we are going to look at today briefly, with the examples, is the one of the providers that participated to the call. So we are able to use this in for that reason.
Nice. And where is the Vega supercomputer and how big is it
Yeah,
roughly?
sorry. Yeah, it's in
Okay.
Slovenia. So we are going to travel a bit from from Italy and
Awesome.
UK, I think. So
Yeah,
yeah.
nice. Cool. So I've also got this diagram that hopefully you can see on my screen here, uh, which kind of describes a little bit how the Interlink project works with Kubernetes and Slurm. Would you mind taking us through this diagram, kind of explain a little bit in a bit more technical detail, kind of what we're going to see before we see it?
Yeah, sure. So essentially, the basic idea is to take a piece of technology that is already there from since a while. That is the virtual kubelet
Mm,
technology that is part of the CNCF already sandbox. So, and that actually emulate the behavior of a normal node in a Kubernetes cluster, and
mhm,
say to the basically saying, okay, hello, I'm a new node, just pretend to be, and it just pretends to be a normal node. But
mhm,
what happens when the schedulers of the Kubernetes cluster delegate one pod or to that node is that it takes the information from there and can do whatever you want. And whatever you want can be, okay, I want to go into a function as a service endpoint and run my
mhm,
container. I want to do whatever. And what we did in Intertwin and in Interlink was driven essentially from the needs that we acknowledge that many HPC centers are like that and won't change any sooner, or at
mhm,
least it takes a lot of effort to include and to customize solutions for a specific HPC center that might not work for another. So
yeah,
our question was, what can we do to abstract all the Kubernetes internals from the equation here and keep on the, if you want, on the right hand side of the
Yeah.
plot here, just the bare minimum APIs to execute a container and follow up with
Hmm.
all the life cycle. So what
And
happens here
that's
is
these
that you
APIs
have,
here, right? On the
yeah,
Interlink
you
API
have an
server.
API
Yeah,
layer.
yeah,
Yeah, essentially, when you do the translation from I want a pod to I want a container with this information,
yeah. Hmm.
just let me know how it's going.
Yeah.
And this translation allows us to attach to different kind of batch systems that are pretty useful in many scientific endeavor. And one of these batch systems also happens to be very the most adopted by many Euro HPC centers. That is the Slurm one.
Hmm.
And how you can use these systems? Yeah, the only requirement basically is to have a runtime for containers available at the
Yep.
nodes.
Hmm.
So that's the only requirements from the provider perspective. But nowadays it's pretty common. So
Yeah.
it's only matter of understanding which one you have. So
So Aptainer and Enroute, like those kind of systems.
yeah, yeah, essentially that. And yeah, it can be others, but these are the two most common. Yeah, for sure.
Okay, perfect. Yeah, uh, very exciting. All right, cool. So let's actually try and get it working. Let's.
Yeah,
So what I've got here is I've got access to um, uh, a virtual. Well, it's a real Kubernetes cluster, but it's a Kubernetes cluster with some virtual nodes, and the virtual nodes exist on that Vega supercomputer in Slovenia, right? And
yeah,
so yeah, we're actually deploying onto this supercomputer, um, and um, and yeah, so this Kubernetes cluster is kind of like a portal to this supercomputer here because we have one of these nodes, which is a virtual kubelet node. Is that right?
yeah, exactly.
That is actually talking um, to that supercomputer there. So what we can do is we already have a Helix deployment running. Um, and that is running, that's running somewhere else, is it? Is that running on a different Kubernetes cluster?
No, that's the cool thing. So I just didn't think that it was useful to tell, but yes, you are in a real cluster, but I'm creating for you a virtual cluster
Hmm.
on the parent. So you're on the child cluster, but the infrastructure for the cloud part is the same. So I can
Cool.
show the Helix instantiation, but you cannot see it.
Ah, that's pretty cool. Okay. Um, so yeah, and maybe we can look at that
But
outer,
again,
we can look at that
if you
outer
want to
cluster
install,
then. Yeah,
yeah,
go ahead.
if you want to install it by yourself later, you can as well. So
Yeah, yeah,
you
yeah.
can do
Nice.
the exercise.
Yeah, that would be cool. So yeah, so that makes sense. And what we have here is so this Helix deployment is actually on the outer cluster, like the kind of the real Kubernetes cluster rather than
Yeah,
the virtual cluster that's on the inside. Um, and what you can see here is that this is a regular Helix deployment, all the different things you can do like chat, image generation, fine-tuning, RAG, and building these AI-powered apps is possible except for the fact that this cluster doesn't have any GPUs connected to it yet. Um, and so so let's fix that. So the way that we do that is we kubectl. Well, actually, let's look at the pod first. So what we're doing here is we have this pod, which it looks a lot like a regular pod specification for deploying a Helix runner. A Helix runner, by the way, in the architecture here, is that you can attach many different GPU runners to the same Helix control plane. And they just connect over the network, which is nice because it means that you can connect these GPU resources from different places and kind of aggregate them into a big cluster, even if they're in kind of different data centers or different deployments. Like, for example, the one that we're going to deploy into Slurm is going to be running on a Slurm cluster and reaching out over the network to the Helix control plane using TLS, so it's secure. Um, so um, so this is a pod spec for deploying a regular Kubernetes cluster, for deploying a regular Helix runner. in Kubernetes, but it's a special pod spec because it has some of these additional annotations. So do you want to explain what these annotations do, Diego?
Yeah, so during the phase where you do the translation, basically you can decide whether you want additional parameters to be passed to the final container executor. So you can decide, okay, if a pod arrives with this kind of annotation, so slurm job dot vk exactly that attach this information to, in the first case, is to the submission command. So
Hmm.
submit a Slurm command with these options, with a partition name, or with whatever. Then you can also tweak the how singularity or obtainer or en route um, mount file systems. So in this case, we have store machine learning models into the shared file system at the center, and then we can mount them directly when we launch the runner.
Hmm.
And then finally, other options to the singularity command. So yeah, you can specify and provide any number of these annotation without compromising how the pod works. So
Hmm.
yeah, the cool thing is that essentially you decide the meaning of these parameters at the last mile. So really at the plugin level where you need only to care about the container and how you run them.
So awesome. And that's really helpful. So we're looking at these annotations, and it looks like this is asking Slurm for a GPU and asking for one node. It's also bind mounting the shared NFS style file system um, into the Helix runner, and it's bind mounting it into the /temp directory. And then in here, we're also telling Helix to look for model weights in this temp cache directory. And so that's really cool, actually, because that means that we're leveraging the shared file system of the Slurm cluster to act as a store for model weights that can be used for many different Helix runners across the system. Is that right?
Yeah, yeah, exactly. So the idea is that usually at the supercomputers, especially for scientific purposes, and yeah, you have a shared file system, and
Mhm.
you can use it for this kind of stuff. So avoiding to download multiple times the models is one of them.
Yeah. Awesome. Yeah, that's very cool. And then this is just a normal kind of Helix runner pod spec, but there are a couple of other changes at the bottom around these tolerations. Do you want to just explain what those are for?
Yeah, the cool thing of these ones are that they are native Kubernetes specifications. So we are talking Kubernetes language to tell, okay, this pod has to go to this special node, that is the Vega node.
Hmm.
But with the node selector by itself, it won't be enough
Hmm.
because by default you cannot run the scheduler cannot schedule any pod on this kind of virtual node because you want to
Hmm.
be sure that daemon sets and whatever are not scheduled on them.
Yeah.
So you have to activate a toleration and exclude
Hmm.
them from the general purpose pods, let's say.
Cool. So, does that mean there's a taint on the? I'm trying to remember how this all works, but does that mean there's a taint on the nodes and then
Yeah,
tolerations on the spec?
yeah,
Okay, on the pod spec. Nice. Great. So what we can do now is we can deploy this pod spec, and I'll deploy the spec, and then we can quickly switch to looking at your screen, and then we can watch what's happening on the Slurm side, if that's okay. Yeah, are you ready? Shall I go ahead and apply the pod? And then I'll
yeah.
stop sharing and you can start sharing quickly. So if we, yeah, kubectl apply -f runner vega.yaml, then that's going to create the pod. And if I look at get pods, I can see that's now a pending pod. So I'll quickly stop sharing my screen and
Okay,
sharing yours.
sharing. Okay, I don't know if you can see that,
Yes.
but yeah.
Oh, it
One
came up.
one
Okay, exciting.
yeah, one job just came up, and then we still is still in queue for some time.
Hmm.
and hopefully soon enough we will have it running.
That's very cool. And so, for anyone who's not familiar with the SQ command, could you just describe what that's showing us?
Yeah, essentially any batch system has its way to check whatever is in queue.
Hmm.
So here we have a job that arrives that wants to run our payload that is a container. Yeah, right now it's running.
Hit
And so
deploy,
you're
yay.
asking for all your jobs. And now since we are dedicated to this demo, I have only this job running. And
Hmm.
so yeah, I can stop sharing maybe. You can check if the dashboard shows something.
Cool. And I'll share
Okay,
my screen again so you can see it.
okay.
So we should, yeah, from the Kubernetes perspective, we should now see that that pod is running, and it is. It's been up for
Yeah.
75 seconds. And I should
If you
even
are
be able to
brave
see all the
enough,
logs.
you can also do exactly the log.
Yeah,
Okay.
nice. So that's showing us, yeah, it pulled the Llama 3 instruct model, and I think it already had the Llama 3.1 model there
Yeah.
on the file system. So that's cool. So we'll be able to use the Llama 3.1 model. And then if we go and look inside that actual Helix deployment, then this is awesome because we can see that yeah, runner Vega has already come online and is ready to take inference and fine-tuning workloads. So what I'll do is I will put these side by side so we can look at the dashboard while we do an inference. So we put the dashboard there, then we can go in here, make a new session, and we've got this Llama 3.18b, and we can say um, hello to the model. And so what you can see there is that that's immediately setting the desired state of the cluster to these two slots to say like please provision two Llama 3.1 instances, um, and then the actual state is updating, and you can see that we've got this 11 gigabytes of GPU memory, 100% scheduled on the GPU. And then it went and started the second model as well, and then it responded to us. So it took a few seconds to start up that first time, but now if we say, "Are you quick?" you see it's lightning fast, and it's got an attitude as well, which is funny. So yeah, we now that these models are warm, that they're loaded into GPU memory, they'll be super quick. And actually, this is amazing because this is like accessing this super high powered GPU infrastructure on this supercomputer, and the networking is awesome. The GPUs are performing well, and um, this is yeah, it's connecting this world of generative AI with this world of high performance supercomputing. And delivering really high quality services as a result of that. Um, so yeah, so this is pretty cool that we can do inference with Helix. But what would be even cooler is if we could show that we can integrate Helix with an external API. So let me try and do that. What we're going to do is we're going to go in and create a Helix app, um, and we can integrate with an API for looking at currency exchange rates, because that's a good example of like live data that you want to have like up to date information in your LLM. And of course, your LLM was trained months ago by Meta or whatever, so it's not going to know about the current exchange rate. So we can use APIs to feed in up to date live information. So let's say we've got this exchange rates app, um, and we can hit save there. We can tell it, tell the user about exchange rates. Um, and then we can say, let's test the app. This is going to show that it doesn't work yet because we haven't plugged it into an API. We can say, what is the current euro to uh, British pound exchange rate? Um, and it says, as of my knowledge cutoff, the exchange rate is approximately that. But I happen to know that's not right. Um, and what we can do is we can actually make this app work by integrating it with an external API. So if you go into integrations inside this Helix app editor and click Add API Tool, then you can plug in an exchange rates API. Um, and this works with any API that has a Swagger spec, like an open API spec. We can hit save there, and we can say, we can ask the question again, what is the current euro to pound exchange rate? What it's going to do now is it's going to make an API call to that external API, and it's going to give us the correct rate, which is that actually 1 euro is 0.82 pounds. So that's pretty cool. That was like really easy to plug in an exchange rates API and get good information. But what I want to show next, which is the kind of the next level beyond, okay, I can prototype this app quickly. What I want to show next is kind of what the next level is beyond that, which is how can you ensure quality of that application and do testing of that application? Because if we're just doing software development, then you wouldn't want to ship your software into production without tests. And if you're developing Gen AI applications like this, you also shouldn't ship those into production without tests. So what I can show you is that if we go to the developers tab inside the Helix app editor, that this application is actually accessible as an AI spec YAML file. So we can now, we've already got 2 YAML files that we're working with. We can add a third YAML file, which is the actual AI application itself. And then I can also show you how we can configure the Helix CLI to talk to this cluster that's actually running on Slurm infrastructure, or at least the GPUs are running on Slurm infrastructure. So the way I do that, I'm going to go ahead and call this exchange rates.yaml and paste that in. The way I do that is I go into my Helix deployment, just make the screen a bit wider. Go into my Helix deployment, go to account and API, and I'm going to install the CLI, which works on Windows, Mac, and Linux. And that will just take a second to download. And then I set the authentication credentials to connect to this cluster running in the INFN Kubernetes infrastructure. And then I can do Helix app list. And you can see there's that exchange rates application that I deployed in the cluster there. So if you're familiar with Kubernetes, this will also seem familiar. You can do Helix apply-f on that exchange rates app, and it will go ahead and update or deploy the application into Helix. And then you can see it here in the App Store. We can see we've got this exchange rates application. So I've actually got another couple of example YAMLs that I'm going to refer to here. The testing Gen AI YAML that we have, we've got this repo on GitHub. I'm going to give you an example, a slightly simpler example for the purposes of this demo of a comedian. Now I'm going to have a comedian. Let me see. Yeah, I'm going to deploy this comedian. So we can now deploy the comedian app into the supercomputer. I never thought I'd say those words. And if we go and look in the App Store, then we've got this comedian who tells jokes. One of my favorite comedians, Bill Hicks. And we can say, hey, oh, interesting. I need to update the model name, which is fine because we have a different model in this cluster. So let's go and do that. Again, it's kind of nice that you can version control changes to the model. I'm going to say fix model. I didn't set up a remote yet. I'm going to Helix apply-f the comedian, and we should be able to see that that works. Hey. Oh, it works. Okay, cool. So the comedian's talking to us, but the comedian is not telling me jokes. I want the comedian to tell me a joke every time I say anything to the comedian, and the comedian is not currently doing that. So let me show you how we've actually already got a failing test for that case. We want the comedian, every time the comedian says anything, we want the expected output to be a joke, and it must be an actual joke. Um, so what I can do now is I can do helix test dash F on the comedian. And what that's going to do is it's actually going to run tests um, against the supercomputer that checks whether the comedian is funny. Um, and that loaded up this browser, and we can see that we failed the test because the response does not contain a traditional joke with a setup and punchline, but rather a casual greeting and an invitation to conversation. So just like we would do normal software development now, we can try and make that test pass. So let's go back in here and edit the comedian. And we can say, how are we going to make that test pass? Well, we can say you are funny. Tell a joke on every interaction. And now we can run the test again. And then we can look at the report. And now it passes. So that's pretty cool. I said, hey, and it said, why did the coffee file a police report? Because it got mugged. Um, so yeah, this is just kind of a little insight into how you can do test-driven development for Gen AI applications. But the really cool thing about this is that this was all running on this HPC supercomputer. Imagine that we're not just creating like a comedian chatbot, but we're actually building serious scientific LLM applications. And so we could put custom knowledge into those applications. We can integrate with internal APIs, and we can run it all on HPC infrastructure. And you could actually build these AI applications that help advance scientific exploration and advanced humanities understanding of science faster. So yeah, I guess that's kind of the demo. I think to recap, what we've got here is we've got a system which has deployed Helix on Kubernetes infrastructure on one side, but is bridging that Kubernetes cluster to a Slurm cluster to existing HPC infrastructure. And so when we look at the Helix deployment, we've got the control plane and the authentication and the APIs running in Kubernetes, but we've got the actual GPU infrastructure being provisioned from the underlying Slurm infrastructure, like we saw on Diego's screen when he was showing us the SQ command. And we're able to build serious LLM-based applications on top of this stack. So yeah, anything you want to add, Diego, or any comments or thoughts that you want to finish with?
No, I just found pretty cool the demonstration of the task, so I think it would be very nice. Also, the nice thing of this implementation is also that if you can go back to the sharing,
Yeah, yeah, sure. I'll share
you
my
can
screen.
imagine that you can also have all the control plane, all the blue part can also be on your laptop and still sharing
Hmm.
the very same infrastructure on the orange part, okay? Because
Hmm.
the delegation is actually over HTTP with OIDC authentication. So if you're
Hmm.
authorized to use that account to go to the Slurm cluster, you can also have your instance on your laptop of
Yeah,
Helix, and you can manage to talk with the supercomputer. So yeah,
yeah,
just
that's awesome.
another
Very,
possibility.
very cool. Nice. Yeah, you can imagine that the Helix deployment is running in a kind cluster on your laptop,
Yeah.
and then you're sort of bursting out to the supercomputer to provision GPU resources on demand, and that those model weights that on the supercomputer are all cached on the shared file system already, so you can very rapidly deploy these runners and access even like massive models like the latest Llama 3.3 70B models and whatever else comes out in the next 6 months, which is going to be an exciting time for open source AI. So yeah,
Yeah,
great.
correct.
Awesome. Well, thank you so much, Diego. Thank you for joining me today.
Thank you.
And yeah, it's exciting to share what we're working on. And thank you so much for all your help.
Thank you for having me. Bye bye.
Cool. Thanks. Bye.